Okay, this video will talk about the scalar product of two vectors. This is called the scalar product, also known as the dot product. Okay, so there's two names for the same operation, and we'll be looking at what this is. Okay, so let's back up a little bit. If you recall, we know now how to, if we have two vectors A and B, we know how to add them, we know how to subtract them, and we also know how to perform scalar multiplication on a vector, right? We know how to multiply a vector by a scalar, and we know how to flip it, okay? Because we can multiply by a negative number, okay? But we haven't really talked about multiplication of vectors, okay? We can't really multiply two vectors together like we do in regular algebra. So if I have A, if I have A and B, and I just say, well, what would that be if I multiplied it with C and D, okay? How would you do this? It would be kind of difficult, right? So you might be tempted to do, just some sort of multiplication here, but okay, we don't, this type of regular normal multiplication does not exist in vector algebra, okay? So what we do have though is a special type of operation called a dot product or a scalar product, and this is a special operation, and there's a formula for it, okay? And let's just go right into it, okay? If I have two vectors A and B, where A has the components A1, A2, and B has the components B1, B2, then the scalar product, okay, remember this is an operation that I'm doing to these two vectors, okay? The scalar product, also known as the dot product of A and B, is defined as, okay? We define the dot product to be A dotted with B, okay, so I'm going to read this as A dotted with B, or also you can read it as the dot product of A and B, okay? The dot product of A and B. So these are the two ways you can read this, okay? The dot product, A dotted with B, is the components, the x components, A1 times B1, the x components multiplied together, plus the y components multiplied together, okay? A2 and B2. So that is how we perform the dot product on two vectors. It's not a very intuitive operation, but just know that this is how we find the dot product, and it does have a use, okay? We'll talk about that in a little bit. So let's just practice doing the dot product first. If I have 4, 3 dotted with 2 minus 3, what is that answer going to be? Okay, so we're gonna take the x components, multiply them together, so we have 4 times 2, and then we're gonna add the y components multiplied together, so 3 times minus 3. Okay, and if we do this, then we end up with 8 minus 9, and we end up with minus 1. Okay, so the dot product here, when I find these two vectors and then I take the dot product of them, I get -1. Kind of interesting, okay? I'm not getting a vector, this is a scalar, okay? This is a scalar value. So that's something that's not very intuitive, but it's what we get from this operation. Okay, let's try another one. So this would be what? The dot product of these two vectors would be -7 times 1 plus 4 times 5, which is 20, so that would be 13. Okay, so 13 would be the dot product. This is the dot product. I guess I should write here scalar quantity. Okay, but this is the dot product of these two vectors. Okay, these two vectors, -7, 4, and 1, 5. So there you go. The dot product is a scalar quantity. Okay, please write that down. The dot product of two vectors is always a scalar quantity. If I somehow do this and I end up with like a vector, if I somehow do A dotted with B and I end up with a vector with something here and something here, then I know that I'm wrong. okay? So please check your work, okay? Make sure that you get a scalar quantity. Now I do want to mention here a little bit more about this symbol right here, okay? That's a fat dot. Okay, notice that this is a fat dot and this is a fat dot. Okay, so make sure that you use a big, dark dot when you're doing your notation, okay? This represents the dot product. Okay, that's the dot product, or the scalar product. Okay, so please make sure you do that when you are writing in your books. And please don't forget also these arrows on the variables that represent vectors. Okay, now let's talk about the uses of the dot product. Okay, how is this useful? Why is A dotted with B ever going to be useful in a real-world situation? Okay, well it actually helps us find the angle between two vectors. Okay, that number itself is not the angle, but it helps us. It helps us find the angle between these two vectors. So let's say I have vector A and vector B. Remember that vectors can be moved anywhere in the plane. Okay, they can be moved anywhere as long as I don't tilt them or change their length. So if I move A and B together, then they form a plane, right? And I can find the angle between those two vectors, okay, in that one plane that they formed. So this angle can be found by using a special formula, and this formula. This is cosine of theta is equal to A dotted with B. So this is where we actually use the dot product. We take the dot product, or the scalar product, of those two vectors and then divide it by the magnitudes of each of those individual vectors. So in order to find the angle here, I need to find the dot product of these two, and I need to know the lengths of these two. And then I actually need to be taking the arc cosine there to find the angle. So you would probably need to use your calculator here unless your numbers were really easy. Okay, so let's try an example here. P is 3, 1, and Q is 2, minus 1, and those are both vectors. What is P dotted with Q? Okay, so we know how to find the dot product. The dot product of P and Q would be 3, 1 dotted with, remember, notice I'm putting a big dot here, 2 minus 1. Okay, and so that would be 3 times 2, which is 6, plus 1 times minus 1, which is minus 1, so that would be 5. Okay, so 5 is the dot product. But now I need to find the angle, so I'm going to use my formula up here. Okay, this formula right here that you should have written down, and I'm going to go cosine of theta is equal to the dot product of, well, let's use P in this case, P dotted with Q divided by the magnitudes of each of those individual vectors. And notice here that on the bottom I have a scalar quantity times a scalar quantity, and also on the top I have a scalar quantity. So this whole side becomes a scalar quantity, and then I can use my calculator to find the inverse cosine of that. Okay, so I know that P dotted with Q is 5, but I don't know what these two values are. Let's find what these two values are. Okay, so the magnitude of P is the formula 3 squared plus 1 squared, which is the square root of 9 plus 1, which is 10. Okay, and the magnitude of Q is going to be 2 squared plus minus 1 squared, which is 4 plus 1, which is square root of 5. Okay, so now I have these two values and I have this value. I can plug it into this formula, and that will hopefully help me lead me in the right direction. This is going to be 5 over root 10 root 5. Okay, what is root 10 over root 5? Root 10 over root 5, that's root 5 times root 2. So root 5 times root 5 will just become 5. So I end up with 5 over 5 root 2, and I'm left with a 2 there. This becomes, those cancel out, so I'm left with 1 over root 2. Hey, there's a nice number, so I actually don't need a calculator here. Cosine of theta equals 1 over root 2. What is that? Well, on my unit circle, that's going to be that's a special triangle. That's right. That's root 2 over root 2, or sorry, root 2 over 2. and it's positive, so it's going to be 45 degrees right there. So theta would be equal to 45 degrees, and that would be the angle that I'm interested in. So that would be the angle between P and Q. Okay? Let's try one more example. The two vectors A and B are perpendicular. This is the symbol for perpendicular. Okay? Perpendicular meaning that they are forming a right angle. Okay, find T. Okay, now I didn't really talk to you about this in depth, but let's go back to the cosine of theta. Okay, let's go back to this formula. Okay, if I have this formula here, and theta, let's say this was 90. What's going to happen to this at 90? What is cosine of theta when theta is, or sorry, what's cosine of 90? Okay, cosine of 90 is right here, right? That's going to be 90. Right there, the cosine value is 0. Okay, so 0, when theta is 90, this becomes 0. So this whole side also becomes 0, which means that if the dot product is 0, okay, then my cosine of theta is, my angle is 90, okay? So this is another rule for you to write down. A is perpendicular with B, these two vectors, when my angle is 90 degrees, and if this is true, then the dot product is equal to 0. Okay, so here's the connection right here. The dot product is 0 when the angle is 90. So in order to find perpendicular angles, or sorry, vectors, or in order to check to see if two vectors are perpendicular, then we need to find the dot product, and if I end up with 0, they are perpendicular. Okay, so let's just rewrite this. A is perpendicular to B if A dotted with B is equal to 0. And so this is the real crux. This is the rule that I want you to remember. Okay, so let's use that over here. Let's use that over here. What is T going to be if I know that these will be these vectors are perpendicular? Okay, so in order to do that, since I know I need to use a little bit of logic. Since A is perpendicular to B, then their dot products must also be 0. Okay, their dot products must also be 0. So I can find the dot product of these two and set it equal to 0 and solve for T. So what's A? 2 and minus 5 dotted with T 3 should be equal to 0, right? So I need to solve for T. Well, this becomes 2T plus 5 times 3, or negative 5 times 3, so that would be minus 15 equal to 0. So that becomes, actually, sorry, this should be minus 3. But let's just do it like this for this example, okay? So 2T would be equal to 15, so T would be 15 over 2. Okay? So if I have T is 15 over 2, which is about 7.5, okay? If T is 15.2, or sorry, 15 over 2, then that would make these two perpendicular. Okay? So there you go.